Hello students, in this video we are going to discuss pulse time modulation. In the last video we have discussed pulse amplitude modulation generation and detection. Along with that we have discussed transmission bandwidth of PAM, which is greater than FM. Okay, so in the pulse time modulation, it is broadly classified into two types: pulse width modulation and pulse position modulation. First, we will discuss pulse width modulation. These two are related to time. Okay, so that's why these two modulations come under the pulse time modulation. First, we will discuss the pulse width modulation. Okay, as the name itself indicates, here we are modulating the width of the carrier signal, okay, according to the baseband signal or original signal or modulating signal by keeping amplitude and position or constants. Okay, so in the pulse width modulation, we have the user information, right? So that pulse width of the carrier signal varies in accordance with the modulating signal, right? What is there in the pulse width? In the pulse width we have the user information, right, in the form of width variation. Okay, so we will discuss how it will be the pulse width in the form of wave. Okay, how we are generating the pulse width modulation, how we are detecting the pulse width at the end, at the receiver end. Okay, we will see all those things along with the advantages and disadvantage of pulse width modulation. So in the pulse width modulation, by generating, it inculcates noise, additive noise. I have already discussed what is that noise, right? We have different types of noise generates, right, in the circuit, and also while transmitting the signal in the transmission medium through the air, right? For example, electromagnetic interference noise, switching noise, power variation noise, etc. So such type of noise we call that one as a additive noise. These noises, what it will do, it varies the amplitude of PAM signal, right? We can also able to remove this noise by using a limiter circuit. So we will discuss how we are going to remove that unwanted noise signal by using the limiter circuit. We are using that limiter circuit at the receiver side. Okay, so in the um, PAM signal, because of noise, amplitude varies, right? But these amplitude variation because of noise, but this amplitude variation does not affect the performance of PAM signal. Okay, so because of additive noise, it varies the amplitude of pulse width modulation, okay, pulse width PWM signal, but it does not affect the performance of PWM signal because PWM is more immune to noise, which means that variation of amplitude does not affect the width of the pulse. Okay, width of the pulse, just it affects the amplitude of PWM, but it does not affect the pulse, right? So it is more immune to the noise than PAM, because in the PAM what happens? We are varying the amplitude of a carrier signal according to our baseband signals. The amplitude detection at the receiver end is very difficult because amplitude detected means, so once the PAM signal combines with the noise at the receiver end, we are receiving such type of signal, means we can't separate our original signal and noise. We can't able to detect which one is our noise, and this is noise. Okay, this is noise, this is my original required amplitude. Which one is noise and which one is amplitude? It is very difficult to separate at the receiver end where it is in PAM. Okay, PWM modulation technique. But in PWM, even for the noise, the amplitude varies, but it does not vary the pulse width. It does not vary the pulse width. Even if the amplitude affected by noise. Okay, this is because it is more immune to the noise. PWM signal is more immune to the noise when compared to the PAM modulation technique or PAM signal. Okay, so we will discuss how we are going to generate PWM signal. Okay, so with the circuit and waveform. Okay, so we will discuss the waveform everything in the next slide. Okay, so first we will discuss how we are going to generate PWM signal, pulse width modulated signal, pulse width modulated signal. So here we are using the main component is a comparator. This is my comparator. This is in the non-inverting terminal we are applying the modulating signal, that is my original signal or baseband signal. In the inverting terminal of comparator I am applying the sawtooth generator signal, right? So at the output of comparator I will get pulse width modulator output. So that same output, the PWM output, is given to the monostable multivibrator circuit. So we will get the pulse position modulating output. So we will discuss how we are going to generate PWM output by using a comparator. So the PWM output, we can also call that one as a, okay, pulse duration modulation. Pulse duration modulation, or we can also call this one as a pulse length modulation. Pulse length modulation, right? So we have three different names. Okay, pulse width modulation, pulse duration modulation, pulse length modulation. So how we are going to generate this pulse width modulation? By using this circuit. Okay, so in order to generate pulse width modulation, so here one condition is there. So the modulating signal amplitude should be greater than my sawtooth signal, right? Sawtooth signal or sawtooth amplitude of the signal. Okay, that is the one condition. So in order to generate pulse width signal, okay, modulated signal. So as I said before, so sawtooth generator generate the sawtooth signal. Okay, you know very well this is our sawtooth signal, right? This is my sawtooth signal. This is my model. That black color is my modulating. This is my modulating signal, right? So we are, this sawtooth signal is acts as a sampled signal. How we are using there in the rectangular pulse as a, in order to generate pulse amplitude modulated signal as a sampled signal, right? We are used rectangular pulses, but here we are using the sawtooth signal as a sample signal. Okay, as a sample signal. So we are sampling our modulating signal. We are sampling our, this is my modulating signal, this is my sample signal, sampling signal, sawtooth signal. This is my sawtooth signal. So the first condition is my sawtooth signal amplitude should be less than my modulating signal. See here. So this is my sawtooth signal, this is my modulating signal, right? This is my sawtooth signal, this is my modulating signal. This is my sawtooth signal, this is my modulating signal. So that sawtooth amplitude is less than the sawtooth amplitude is less than the modulating signal, right? So which means the modulating signal amplitude is greater than the sawtooth signal. Then only my comparator output is high. My comparator output is high. Okay. So if the sawtooth signal is greater than the modulating signal, means my comparator output is low. My comparator output is low. So I will generate the PWM signal only when my sawtooth amplitude is less than the modulating signal. Then only I can generate the uh, PWM output. Otherwise, my output is 0. Okay. See here. So here my sawtooth sawtooth amplitude is less than the my modulating signal. So I am generating pulse width varied modulated signal. So here my pulse width is very small when compared to this one. How it is varies? How it is varies? It is entirely depend on condition of sawtooth signal and the modulating signal. Especially for the lower value of amplitude of our sinusoidal signal. So I will get minimum pulse width. As the amplitude goes on increasing of our modulating signal, my pulse width is also increases. See here, this is my negative value. This is the minimum value of sinusoidal signal of negative, right? So I'm getting very minimum width of PWM signal. As the amplitude goes on increasing, my pulse width is also increasing, right? So here, this is my positive half cycle. My pulse width is get increases, right? As the maximum positive half wave of the signal, I will get maximum pulse width. I will get maximum pulse width. Okay, as the voltage, as the amplitude of our sinusoidal signal is goes on increases, my pulse width is also increases. The minimum pulse width I will get in the negative half cycle, maximum pulse width I will get at the positive half cycle, especially in the maximum voltage of your positive half cycle. Okay, so in this way, so we are generating pulse width modulated signal. So if we are giving that pulse width modulated output to the monostable circuit, so we will get the PPM signal. This is a pulse position modulated output. So after this pulse width modulated signal, right? So I will get the fixed duration or fixed pulse width and fixed or constant amplitude of rectangular pulse generated after that PWM signal. How we are generating that PPM signal we will discuss in detail while discussing the pulse position modulation generation and detection. Okay, so next we will discuss how we are going to detect the pulse width modulated signal at the receiver side, right? At the transmitter side we are using the generation. At the receiver side we need my original signal. I don't want PWM signal. I need, this is a modulation. I'm modulating the signal, right? So this is a my digital pulse modulation technique. PWM is a one of the my digital modulation technique. So I want at the receiver side my original, how I am going to demodulate my original signal from the PWM signal. We will discuss in this video. Okay, so we will take the circuit and waveform in order to discuss how we are going to generate detect original modulating signal from the PWM signal. Okay, so this is my detector circuit or demodulated circuit of PWM signal. Okay, so here we are using the pulse generator, right? Ramp generator, reference pulse generator, clippers, low pass filter as a circuit component, right? This is the block diagram of your demodulator circuit. Okay, demodulator of our PWM signal, right? I want original signal from the PWM signal, right? So here first we are applying the PWM signal plus noise. As I said, in the circuit itself we will get the noise in the transmission medium. Also we will that PWM signal is distorted by the noise. So the PM signal plus noise is the input of our pulse generator. Okay, so pulse generator, so the pulse generator removes the noise. Pulse generator removes the noise. It gives the only cleared pulse rectangular pulse. That is only PWM signal we will get at the output of pulse generator. We will see the waveform. Okay, this is my PWM signal. This is my noise. These are the noises. These are my pulses. The PWM signal plus noise. So represented like this. Okay. So after sending this PWM plus noise with the pulse generator, I will get the regenerated rectangular pulse, which means we are removing the noisy signal. Just we are retaining my the regenerated PWM wave signal, right? So after that we have used the ramp generator. So here the output of pulse generator, that is PWM, so we are reshaped or regenerated. So PWM signal is a input of my ramp generator. Ramp generator generates the ramp signal based on my output of my pulse generator, right? How it will generate, we will see in the graphical representation. Okay, see here, this is my regenerated pulse. Okay, see here, based on my pulse width, I am going to generate my ramp signal, right? Here, this is my ramp signal, right? This is my ramp, right? R of t is equal to R of t. We are representing R of t, right? So we are representing R of t as the input voltage. As the time increases, the amplitude is also increases, right? So here this is my ramp. We are representing, usually mathematical representation is R of t, right? So here this height of the ramp is determined by the pulse width. The height of the ramp is determined by the pulse width. See here, for this pulse width, the height of the ramp is bigger, right? Somewhat is lengthier. For this pulse width, the height of the ramp is some more higher when compared to this one. This width determines the height of the ramp. So the ramp generator generates the ramp signal based on the pulse width of regenerated PWM signal. Okay, after that what we will do? So we are generating the reference pulse generator. By using the reference pulse generator, we are going to generate fixed amplitude, come in constant amplitude and constant pulse width rectangular pulse we are generating, right? After that what we will do? So the output of ramp generator and the reference pulse generator we are adding at the adder. This is our adder. After adding that, so what we will get? So we will get the output of adder. It is like that. See here, like this. So we are adding this ramp signal and the reference pulse generator. Okay, so you have studied in the signal system how to add the two signals, right? So up to this one we are getting here, up to this one we are getting here. Okay, after this we are getting this rectangular pulse. So up to this one we are getting this ramp signal. See here, after this, this is my ramp signal. It is added with 0. I will get again ramp signal, right up to this rectangular pulse I will get. Okay, after that the remaining half of the rectangular pulse I can generate, right? So again I'm getting the ramp signal. If it is added with this, so here it is 0 only, so this ramp signal is added with 0. So up to this one I will get ramp. So after that this constant signal. So after this one I am getting the reference generated signal. In this way we are generating the signal. So from this one we are going to generate PAM signal. But here we are, because of noise, right? So we have removed the noise and we are retaining only PWM, and by using the ramp signal and reference signal. So here we are going to generate this, we are getting this output. From this one, I want only a rectangular pulse, right? I need only rectangular pulse. So we are getting that, we call that one as a PAM signal. We call that one as a PAM signal because here I have fixed amplitude, fixed pulse width and constant amplitude. I have fixed pulse width and constant amplitude. So here I am not getting the variation of pulse width. Okay, so how we are getting this one? By using the clipper circuit. Using this clipper circuit, I am going to remove the unwanted signal. From this clipper circuit, the threshold level, only, above the threshold level, we are retaining the signal, right? The below the threshold level, we are going to remove the particular signal. We are retaining above the threshold level values of signal. So we call that one as a clipper circuit. So we are removing this one and we are retaining above the threshold level value of the clipper circuit, we are retaining. So we call this one as a PAM pulses. So in this way we are generating uh, our signal. Okay. So from this we are generating the signal. Here we are detecting the signal, right? In this way, so by using the clipper circuit, we are removing the unwanted signal below the threshold level, above the threshold level, we are retaining. This is my pulse signal, PAM pulses. This is my original signal. From this PAM signal, again, we can able to detect my modulated signal. Okay, modulating signal, that is my analog signal. Okay, so I need, that is, we are not here, we are detecting, we are not generating PWM signal. Here we are detecting my modulating signal. This is my P. From this PAM signal, again we are going to find out my original signal, right? Modulating signal. Okay, so we have discussed in the PAM signal how we are detecting my our modulating signal. Again, I won't discuss this one. So now we will discuss what are the advantages and disadvantages of my PWM signal. Okay, so my advantages is it is more immune to noise, right? So it won't affect the width of my pulse. It won't affect my width of pulse because of noise. It only affect amplitude. It's more immune to noise. We can easily separate the noise, right? Noise and PWM signal. Okay, and here synchronization circuit is not required between the transmitter and receiver. Okay, the disadvantage is, as we know that here also the bandwidth is anyway, if we are converting analog to digital signal, the number of bits are more, so we need the bandwidth high. And one more drawback is, as the pulse, right, as the pulse width vary, um, the transmission power also get varies. If you have maximum pulse width, I need maximum transmission power. We have to maintain the maximum transmission power, high, more enough transmission power we have to, we need, right, while transmitting the signal through the transmission medium. Okay, that is one of the main drawback in the PWM signal. Okay, bandwidth as same as for all the pulse code modulation techniques, the bandwidth is always high. These are the two main drawbacks in the PWM signal. In the next video, we will discuss pulse position modulation. I hope you are able to understand pulse width modulation technique. Thank you.